So prime and composite numbers. So we've been talking through whole numbers. So these are numbers 1 and 1, 2, 3, 4, right? On and on. And we've been talking about addition, subtraction, multiplication, and division. And so it's interesting to say, so what numbers can be written as the product of lots of combinations of numbers, or are there ones where there's only one combination? And that's really what we're asking when we look at prime and composite numbers. So I'm going to give you some terms, and some of these won't necessarily be new. So if A equals B times C, so if we were doing this in the last section of multiplication, we'd call it groups, size, and then product. But here we'll say A is a multiple of B and C, and that's because there's some number copies of B so that you get to A, right? So B groups of size C gives you A. So there's somehow a way of writing A as a product of B or C and a number. And then if that's the relationship we have, and I'll give you a specific example in just a moment. B and C we call factors or divisors of A. B and C we can say divide A with no remainder. And we say A is divisible by B and C. So take, for example, 21. So looking at this, 21 is a multiple of 3, 21 is a multiple of 7. 3 and 7 are factors and divisors of 21. 21 is a divisor of 21. We could also say that 3 and 7, 1 and 21 all divide 21. Or we could say that 21 is divisible by 3, or 21 is divisible by 7. And so this is how we use this language. But when we think about factors, we could think about our area model. We could do 1 times 27. Oh, this is factors of 27. No, that's just a typo. 1 times 21. 1 times 21. Or 3 times 7. Or 7 times 3. I'll just keep crossing that off. Or 21 times 1. So these are all the ways that we could make rectangles without any hanging off to make 21, right? Because if we would do 6, we could get 6, 12, 18, and we can only get 3 more to get 21. So when we're thinking about factors, we can think exactly of these rectangles. And so here's an example. It says Tyrese is looking for all the factors of 156. So far, he's divided 156 by all the counting numbers from 1 to 13, listing those numbers that divide 156 and listing the corresponding quotients. Here is Tyrese's work so far. So this first line that's kind of cut off, he said, well, 1 and 156, because 1 times 156 is 156. So those are factors. He's like, well, 2 and 78, 3 times 52, 4 times 39, 6 times 26, 12 times 13, and 13 times 12. And so here it says, should Tyrese keep checking to see if numbers larger than 13 divide 156, or can he stop dividing at this point? If so, why? And then it says, what are all the factors of 156? Well, if we think of our rectangles, we can move from that really long, skinny rectangle to a short, slightly squatter rectangle. And then if we would say do this with the number 16, we would see that we could get to a square. But then we start rotating our rectangles and start making them just taller than they are wide. And so we could think of each of these lengths, 1 and 100, each of these numbers, 1 and 156, 2 and 78, 3 and 52, and so on, as lengths of a rectangle. And notice, once he goes from 12 to 13, 12 and 13 to 13 and 12, we know he can stop. Because that's the point where we start getting this shape repeated, except it's just rotated, right? Every factor pair, and we'll call those that, factor pairs, right? As this first column increases, the second one decreases. And so once we get to this point here, where our factors switch places, which we can call the turning point, as soon as we reach that point, we know we can stop. Because if we find the next one we get to will be 26 times 6, but that was already caught up here because we have commutativity with multiplication. And so as soon as we hit that turning point, we can stop. And so that's what we'll say we'll do when we need to find all factors efficiently. We're going to find the factor pairs, and then we'll stop as soon as we reach that turning point. Now I want to go back because I missed something. At the bottom it says, what are all the factors of 156? Well, we're going to use set notation. So we can say the factors of 156 are, and then we can use a set. That's supposed to be a brace. We have 1 as a factor, 2, 3, 4, 6, 12, 13, 26, 39, 52, 78, and 156. Those are the factors. And we're going to write these in set notation because in the next section we talk about when we're finding the greatest common factors and least common multiples, we'll look at intersecting sets to find those two numbers, the GCF and the LCM. And so here it says find all factors of 198 in an efficient way. Well, this is an example of where we know 1 and 198 is there, and it ends in 2, or there's got to be a 2 because it's even. It ends in an 8, and if we divide that, we get, what, 99? We can try 3, we get 66. Check 4, doesn't work. 5 won't work. 6 won't work. 5 won't work. 6 does work. 6 times 33. And I'm doing this on my calculator as I talk through this so that if you want to try to calculate this as I go, it'll give you time to do so. 198 divided by 8 doesn't work. 198 divided by 9. We have 22. We have 198. 10 won't work. 11. 11 times 18. 198 divided by 12. Doesn't work. 13 doesn't work. 14 doesn't work. 15 won't work. 16. I think we're getting down to our last option. 16 didn't work. 17. Nope. 198 divided by 18. It's 11. And we've reached the turning point, which means we can stop. And then to list those, the factors of 198 are 1, 2, 3, 6, 9, 11, 18, 22, 33, 66, 99, and 198. And so that's our efficient way for finding all the factors of a number. And so it says, consider the number 48. Is it possible to list all the factors of 48? Well, sure. We just listed all the factors of 198. And so we could do this here where we have 1 times 48, 2 times 24. Is it 3 times 16? 4 times 12. 5 won't work. 6 might work. It's going to be 8. 6 times 8. 7 won't work. And so we have 8 times 6, and we reach our turning point. And our prime factor, or all of our factors are 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. And so we can very easily list all of the factors of a number. Maybe not very easily. If we had a very large composite number, it might have a lot of factors. But is it possible to list all the multiples of 48? Well, the first one's going to be 48. And then the next multiple is going to be 2 48s, 96. And the next one is going to be 3 48s, which is 144. And then the next one is 192. And we can just keep counting up by 48 and get a new multiple. So it is not possible, let me switch my color because this is important, not possible to list all the multiples. And the reason for that is because there are infinitely many. We can always just add that number again, add another group of that size, and get a larger multiple. And so there are numbers whose only factors are 1 and itself. For example, 5, its only factors are 1 and 5. 2 doesn't divide it, 3 doesn't divide it, and 4 doesn't divide it. Just like with 31, there are only 2 factors, 1 and 31. And so for any prime number p, its factors are 1 and p. On the other hand, composite numbers are whole numbers with more than 2 factors. So any of the examples we've done so far, here's one, 18, 9. And so the fundamental theorem of arithmetic is really why we've been building up towards this notion of primes and towards factors, because we're going to get to what's called the prime factorization. So the fundamental theorem of arithmetic states, each composite number can be written as a product of prime numbers in one and only one way, except for the order. So, right, like, if you can write 6 as 2 times 3, you could also write as 3 times 2. And so up to that order, it'll always be the same. So for example, 6 is 2 times 3, which is the same as 3 times 2, but that's precise. And notice both 2, its factors are 1 and 2, and 3's factors are 1 and 3, right? Those are both primes because they only have 2 factors. And so let's find the prime factorization of 360. And so in the factoring method, what we do is we just factor 360 into, say, 2 numbers. So 360 is 10 times 36. And then we rewrite each of those as the product of, or we break them down into more and more factors. So 10 is 2 times 5, and then 36 is, what, 6 times 6 times 6 times 6. I mean, 2 and 5 are both prime, and so those are golden. They can come along for the ride. 6 is 2 times 3, and 6 is 2 times 3, which thankfully all are prime, and so those are all of the prime factors. And we'll rewrite this in exponential form. 2, we have 1, 2, 3 of them. 2 cubed times, we have 2 3's, 3 squared, times 5. And if that's the prime factorization, we should be able to go 2 times 2 times 2 times 3 times 3 times 5, and whew, that is in fact 360. And so we call this the factoring method because we just keep breaking the numbers down into their factors. And now we also have what's called the factor tree method. And so this is just another way to keep track of our work. We could still say break it down into 10 and 36. Well, 10 is 2 times 5, and 36 we said was 6 times 6. 6 was 2 and 3, 6 was 2 and 3. And so its prime factorization is 1, 2, 3 2's times 1, 2, 3 squared times 5. And notice we only use the bottom level of the tree. We only use the prime factors. And the reason is because if I would include this 6 too, I would end up getting the product 360 times 6, right? And we want to look at this number. And then we have what's called the slide method, right? You can see how that first method and that method really are the same because all of those numbers are precisely the same. But if we want to do the slide method, we kind of use this upside down division sign. So 360, and let's say I'm going to take a 2 out because I know there's a 2 in there at this point, 180. Because 2 times 180 is 360. I can take another 2 out, and I get 90. I can take another 2 out, and I get 45. I can take a 5 out, and I'm left with a 9. I take a 3 out, and I'm left with a 3. And then once I get all prime numbers, because I have to stop once that 3's there, because I can't factor anything else out, and then I get the same prime factorization. And so these are 3 different ways to organize your thoughts, and you can do whatever works best for you. In the homework, it will specify to do it either using intersection of sets or, no, that's not intersection of sets. It might ask you to find the prime factorization, and it might specify to use, say, the tree method or the factoring method.